Hi, I'm Jan, and I will be presenting some results connecting graph similarity to homomorphism densities. Say you want to do machine learning on graphs. Standard machine learning techniques usually take numerical vectors as their input data. So in order to use these in graph, we somehow have to embed a graph into a vector space. And in order for this to yield meaningful results, this embedding has to somehow respect the similarity of the graphs. So similar graphs should be mapped to points that are close. And however, as you notice, it's actually not really clear what it means for graphs to be similar. An example of such an embedding are these Weisweiler-Liemann graph kernels. These have been introduced a while back, and they are based on the color refinement algorithm. The color refinement algorithm computes a canonical coloring of the vertices of a graph, and as you can see here, then you can take these colors and embed the color counts into a vector. And to get a better understanding, let's check out a demonstration of color refinement created by Holger Dell. For color refinement, you take a graph and color all its vertices with the same color. And then, in every refinement round, two vertices get different colors if they have a different number of neighbors of some color. So for the first round, this means that vertices are distinguished based on their degree. And from there, you continue like this until you reach some point a stable coloring that doesn't change anymore. So now you can see these colors on the right and their counts, and we could embed this into a vector. So this would be our embedding. However, we can also use color refinement as an isomorphism test. Take two graphs, compute the colorings in parallel, and then compare these color patterns. If they don't match, we know that these graphs are not isomorphic. However, if they match, they still might be non-isomorphic, so we don't really know. The main advantage of the Weisweiler-Liemann graph kernel is that it's actually very efficient. You can implement color refinement in something like n times log n, and additionally in practical evaluations, these kernels have shown to work pretty well. However, graph embeddings in general aren't really well understood from a theoretical point of view. And one thing many of these have in common, that they are actually based on counting substructures. And the most general way of counting substructures is by counting homomorphisms. As you know, a homomorphism is a mapping vertex between the vertex sets of two graphs that preserves edges. And homomorphisms turn out to be some kind of basis for counting substructures. For example, if you want to count subgraphs, well, these are just linear combinations of homomorphisms. If you want to count these color refinement colors, well, these are just linear combinations of tree homomorphisms. So, on the graph similarity side of things, the most intuitive notion of similarity is probably the edited distance, the number of operations you need to get from one graph to the other. However, it's hard to compute, and it really doesn't reflect the structural similarity of graphs well. For example, random graphs are similar from almost every aspect, but they have high edit distance. And another way you can approach similarity is from this system of linear equations. This system of linear equations encodes graph isomorphism, and the non-negative integer solutions are just permutation matrices encoding isomorphism between two graphs. So if you take a matrix norm and minimize over the set of all permutation matrices, this gives you somehow a similarity measure. However, here the minimization over the set of permutation matrices is still hard. And this is why Grohe proposed the relaxation from permutation matrices to doubly stochastic matrices. The set of doubly stochastic matrices is a convex set, and this yields a convex optimization problem, which, depending on the norm, you can compute using standard techniques in polynomial time. Now, Grohe didn't come up with this out of thin air, because there's actually this theorem by Tinhofer, which states that graphs are not distinguished by color refinement if and only if the system of linear equation has a non-negative real solution, and these solutions are then called fractional isomorphisms. So the graphs of distance 0 are exactly those that are not distinguished by color refinement. However, now this seems completely arbitrary for a graph similarity measure. So let's take a look at the homomorphism side of things. So on the homomorphism side of things, the first result connecting graph homomorphisms to similarity is this rather old theorem due to Lovas, which says that a graph can be characterized up to isomorphism by counting homomorphisms from all other graphs into it. And this gives the idea of taking these homomorphism vectors as an embedding. So for example, if you take the class of all graphs, then we get this infinite vector, which characterizes the graph up to isomorphism. Recently, people have been considering restrictions of these vectors. So for example, if you take the class of trees, count only homomorphisms from trees, then two graphs are mapped to the same vector if and only if they are not distinguished by color refinement. So these results just state what happens if two graphs are mapped to the same vector. They don't tell you anything about what it means if two graphs are mapped to similar vectors. However, in the theory of graph limits, there's this result regarding the cut distance and homomorphism densities, normalized homomorphism numbers. And this informally states that the cut distance is small if and only if these homomorphism densities are close. And up to now, this was the only result giving an approximate relationship between similarity and homomorphisms. And now the result I'm presenting gives us that if we define the tree distance of two graphs by just adding the normalization factor to this convex optimization problem, which we've seen before, and choosing as our norm the cut norm, then this actually isn't arbitrary at all, but we get precisely the correct relaxation of the cut distance to tree homomorphisms, or call it the color refinement relaxation, or the fractional isomorphism relaxation, and we prove that this tree distance of graphs is small if and only if these tree homomorphism densities are close. To understand this result, we first have to understand the cut distance. And the shortest way of defining the cut distance is via fractional overlays, where a fractional overlay is basically just a scaled doubly stochastic matrix. So instead of 1, all rows sum to 1 over n, where n is the number of vertices of G, and all columns sum to 1 over m, where m is the number of vertices of H. And then the cut distance is obtained by this definition, where we minimize over all fractional overlays and maximize over all these cuts. So a fractional overlay, just as the name suggests, allows you to map a fraction of a vertex to a fraction of some other vertex. And you basically can think of this as blowing the graphs up. Here you can see a blow up of 2, and then aligning them as well as possible. And then this maximum just compares the cuts of the graph. So you compare the edge densities between all cuts in our graphs. This is the cut distance. And one observation you can make from this definition is that if you restrict these cuts Q and R such that U sums over all vertices of H and J sums over all vertices of G, then we actually get the tree distance. So what you see here is the definition of the tree distance for graphs on two different sizes. Here you see the counting lemma, which is one part of this result which I've only informally shown to you earlier. And it says that if the cut distance is small, then these homomorphism densities are close. And proving this is not that hard. It's basically a telescopic sum argument where you sum up over all edges of F and then consider that it's mapped, this edge is mapped to G or that it's mapped to H. This is why you have to consider these cuts in our graph. Now, in contrast, proving the inverse counting lemma, which says that if these homomorphism densities are close, then the cut distance is small, is actually very hard. Let's take a brief look at the theory of graph limits, which basically started with this first result of Lovas, which I've shown to you. So you can call a sequence of graphs convergent if these sequences of homomorphism densities converge for every graph. And by the result, which I've just shown to you, such a sequence is convergent if and only if it converges in the cut distance. This is one part of the theory of graph limits. However, what's still missing is that if you have a sequence of graphs, the limit object might not be a graph. So think of it as if you have a sequence of rational numbers, the limit might be an irrational number, like square root of 2. And in the same way, you need the completion of graphs to also capture these limit objects. And this is where graphons come into play. So a graphon is a symmetric measurable function. And if you have a graph, you can just take its adjacency matrix, like you see here, and then think of it as a picture-to-picture. So black means 1 and white means 0. And then this is the graphon representation of this graph. So these are graphons, and all the usual notions like cut distance and homomorphism densities actually directly generalize to graphons. I'm not going into the details here. For the result that I'm presenting, graphons are actually very important, and the reason is the compactness theorem. If we identify graphons of cut distance 0, then we obtain a compact metric space. Now let's assume that we have some pseudometric that is somehow the pseudometric for a class f of graphs in the following sense. So first of all, it's the relaxation of the cut distance. If a sequence converges in the cut distance, it also converges in our pseudometric. And second, the graphons of cut distance 0 are precisely those that have the same homomorphism densities from graphs in F. And these conditions actually suffice to prove both a counting lemma and an inverse counting lemma. So the first point is the counting lemma, and it says that if our pseudometric is small, then these homomorphism densities are close. And the second point is the inverse counting lemma. If these homomorphism densities are close, then the pseudometric is small. And to prove this, you only need the compactness theorem and the counting lemma for the cut distance. And this is actually not hard to prove. If you want to take a look at the details, you can find it in the paper, but this is just a standard compactness argument. You assume that the theorem doesn't hold, and then you get a sequence of counterexamples. By the compactness, you get a subsequence that converges to some limit graphon. By the first condition, you know that it also converges in our pseudometric. By the counting lemma, you know that also these homomorphism densities converge, and then you can apply the second condition to the limit graphon to derive a contradiction. So this means that if you define your pseudometric on graphons, and if it is reasonably defined, then from this exact correspondence to homomorphism densities, you get an approximate one for free, basically. Now, in order to apply this theorem for the tree distance, we of course have to define the tree distance for graphons. That's the important part. Without graphons, you can't use the compactness theorem. Luckily, such a characterization of fractional isomorphism for graphons has been proven by Grabick and Rocha. So if you recall the old statement, then these adjacency matrices become these kernel operators, and these doubly stochastic matrices become Markov operators. But other than that, the statement basically stays the same. Then this allows us to define the tree distance of graphons. So you just take the infimum over all Markov operators and then basically take the cut norm of the operator. And you can verify that this actually specializes to the definition for graphs which we've seen before. So if you view G and H as graphons, then these notions are the same. Furthermore, you can verify that we still have these two properties, that the tree distance is bounded by the cut distance, and that the tree distance is 0 if and only if these tree homomorphism densities are the same. Then we can apply the theorem and obtain that, well, the tree distance is small if and only if these tree homomorphism densities are close. And furthermore, instead of the cut norm, we can also use the operator norm, which in the case of graphs corresponds to the spectral norm. This is particularly interesting because convex optimization in the spectral norm is just a standard application of the techniques from this field. So if we use the spectral norm instead, these results still hold, and we can compute the tree distance and approximation in polynomial time. So we have seen the tree distance, but we can actually use our theorem for graphon pseudometrics in more cases. For example, in the case of path. Delcro and Rattan have proven this characterization of path homomorphism counts via real solutions to this system of linear equations. So non-negative real solutions correspond to tree homomorphisms, and real solutions correspond to path homomorphisms. And the argument is basically a spectral argument, because you can express these path homomorphism numbers by operator powers, and this argument basically directly generalizes to graph forms. You can find all the details in the paper, and using this generalization then you can define the path distance of two graph forms. And then again you can verify that these conditions that we need for our theorem are satisfied, and you also get that the path distance is small if and only if these path homomorphism densities are close. Another candidate for a tree pseudometric that came up while studying this pseudometric is the color distance. So if you want color refinement on a graph, then you can consider the invariant computed by color refinement, that is this graph on these color classes whose edge weights are the edge densities between these color classes. And we can just take these invariants, and since they are weighted graphs, we can compute their cut distance. Then you immediately get that two graphs have color distance 0 if and only if their tree homomorphism densities are the same. And now you might wonder, okay, how does this relate to the tree distance? And while you can prove that the color distance is an upper bound for the tree distance, you can also find a sequence of graphs which shows that proving the converse is actually not possible. So this sequence of graphs converges the tree distance, and the homomorphism numbers converge for trees, but it does not converge in the color distance. So you construct a sequence of graphs such that their invariants are these triangles in the middle, and then the sequence converges to the triangle, but it does not converge to the invariant of the triangle. And this also shows that it's actually possible to construct invariants that converge to a non-invariant. So this counterexample also answers an open question of Grabeck and Rocha, because they defined the graph analog of these invariants and wondered whether the set of these invariants is closed. Well, as we've seen, it is not. You can actually prove a stronger statement that is connected to this inversion problem. So given a weighted graph, you want to decide whether it is an invariant, and if it is an invariant, you want to compute an original graph for it. And the first inversion algorithm was given by Otto. It works for arbitrary structures. And a much simpler linear time algorithm that only works for graphs was given by Kiefer, Schweitzer, and Selmer. And you can take their construction and turn it into an approximate inversion algorithm. So basically you just round the edge weights and the vertex weights of a given graph such that you obtain a valid invariant. And depending on how much vertices you're willing to spend, you can get as close as possible. So for us, this means that you can approximate an arbitrary weighted graph by such an invariant. And since you can approximate an arbitrary graphon by a graph, we also get that the set of these invariants is already dense in the set of graphons. So this brings me to the end of my video. I've introduced this tree distance and shown that it's small if and only if these tree homomorphism densities are closed. Before that, it was only known that it's 0 if and only if these tree homomorphism densities are the same. And by these general results on the graphon pseudometrics, you also obtain a similar result for paths. Now, there are many open research questions which one can consider. For example, our results, since we use compactness, only yield non-quantitative relationships. So can you somehow prove a quantitative counting lemma and an inverse counting lemma? Another open question could be to consider these equitable partitions. Color refinement can be characterized in terms of equitable partitions. So can you somehow characterize the tree distance in terms of equitable partitions? This is also related to the next question. Can you somehow turn color refinement into an algorithm for computing the tree distance? So we know the tree distance with the spectral norm can be computed using these convex optimization techniques. Can you somehow find a direct algorithm for computing it? And finally, something that I've been working on are these k-Weisweiler-Niemann distances. So the k-Weiss-Walter-Liebman algorithm is a generalization of color refinement which colors k tuples instead of single vertices, and you can actually generalize this to graphons and then use our theorems to obtain a hierarchy of these similarity measures. So that was my video. Thanks for watching.